What's up, everybody? Welcome to Fountains of the Great Deep, Part 2. Today we're going to be focusing on oceanic trenches, subduction, the ring of fire, and I've titled it the compression event because it's the time that the waters of the earth, stop increasing, and then the mountains rise catastrophically, causing the oceans to go into the low places, into the basins today, which are the oceans. So that's what we're going to be talking about. If you want to join the stream, hop in the box and uh, talk about the seminar with me. And then after the seminar, of course, we can just share open thoughts on anything, the open mic section of basically all the live streams that I do. So don't forget to like, share, and subscribe to the channel if you haven't already. I will be with you shortly. How did Mount Everest form? Was this a slow or a rapid formation of this giant mountain? According to the modern, theories of plate tectonics, the seafloor was spreading over millions of years. In the process, uh, the oceanic crust is subducting underneath the continental crust. So this is happening over the course of millions of years. That's what's taught in the textbooks. Where the hydroplate theory would suggest a sliding event of the continents removed of their lubrication and compressed from the resistive force and folded the crust. And so this is where basically how I briefly discussed in part one of the presentation, the mantle is uplifting and causing the crust to slide off. So breaks the initial uplifting of the mantle will separate it into thousands of, or hundreds of plates all over the continent. It's going to crack it like an eggshell, basically. But then, the major plates like North and South America, uh, Africa, Eurasia, those will separate as like major plates, even though individually they have several plates of their own, like fault lines and stuff. But the point is that this rapid uplift of the mantle, is causing a sliding event of the crust. And so you have a rapid formation of Mount Everest, about a 6-month process, I would say, or it looks like 4 months. I don't know the exact details. We have in the flood account 40 days of rain, 110 days of rising water after the 40 days of rain, and then several months of assuaging. The water is going back and forth because the mountains are rapidly uplifting. This is to basically stop the earth, from being flooded by water. The waters are increasing for 110 days, and after that, it stops. And what stops it is this rapid formation of the continents. The mountains uplift, all of that water then just basically with gravity flows down into the low places. And this process is several months of the sway going back and forth, as the mantle rapidly uplifts and causes the continental plates to slide off. So, where did all the water go? Is the wrong question. Where did it come from? Is a better question. Mid-oceanic ridge is a scar that the flood left behind. A 46,000-mile mountain range wraps around the world like the seam on a baseball, has a wide intersection in the Indian Ocean directly under the Himalaya Mountains. It was formed from the rising mantle. And that is a undisputable fact that there's a mid-oceanic ridge. It's a huge mountain range, and that helped. It's the main factor in forming the continents, because that will let's give you a better picture of it. Here's the ocean floor. You have the continental shelf to the left, then you have the continental shelf to the right. But to the right, you have what is known as a huge trench. You have a slope before that, rapid decline, drop off point, and then even bigger one called a trench. And this is where the oceanic crust that you see there is buckling down and going under the higher continental crust. Now, towards the center of the ocean, you'll see the mid-oceanic ridge. It's the mantle material that's reached the surface of the ocean floor. And so the idea is that continues just for millions of years. The mantle will eventually, build up, and that part of the ocean, will rise above sea level over millions of years, separate into continents, and then those will develop their own mid-oceanic ridges. Okay, because you have to have an origin of the mid-oceanic ridge, like where did this all start? And so this is kind of like, I would say, the second, I don't know if you could call it, I don't know what you would call it. We'll move on. So you have the liquid inner core, right? Or outer core. Now that will flow up like a boiling pot of water. The heat goes up and it flows across the surface as it cools, and it goes back down. And so this is what they believe, that the mantle is actually doing a circulating underneath the oceanic crust, and it's pulling it down over here where the continental crust overlays it, kind of buckles it down, helps to subduct it over millions of years. So if it starts from a molten state, you have this process occurring where the surface develops a hard and brittle rocky crust, and then the mantle underneath it being circulated kind of causes it, to break through the surface and rise above sea level, and it begins to be separated into different plates as, because different material develops once the mantle surfaces to the earth. It flows across it, and then millions of years of erosion, and it develops kind of into its own continent if you're looking at it from deep time perspective. But it's the idea of what's happening, the convection. Seismic waves traveling through most of their path in the seismometer. First, you can send seismographic waves or whatever through the earth, down into it. You can tell kind of what you're dealing with, if it's a solid or if it's a liquid. And so the mantle, according to a lot of measurements that have been taken, consists mostly of hard rock. And the crust above it is a different kind of rock, but it's still rock. It's a granite, and the mantle would be like I forget what it is, some kind of olivine and something else, but maybe some nickel, but still rock. And some would say that it's like a putty consistency that's circulating. But I don't think that that's really what the seismographic um, record shows. But here you have today will be the crust of the Earth, continental plate, the granite rock, which we're standing on. Okay, sedimentary rock, but far beneath that is a basement rock, which is mostly granite. And then you have under that what is a part of the oceanic plate, the basalts. And then below that, you would have, which is in the red, you would have the mantle. Now that yellow area kind of connects the basalt, with the mantle. And so obviously no one's ever been to the mantle by drilling or whatever. We haven't really even scratched the surface, I don't think, but nowhere close to reaching the mantle. But in the flood model, most of the water that we see today on the surface of the earth came from that yellow line, that region. And so what we see today, is much different from the time of the flood. I'm going to make sure that this audio is good so that, because if I'm muted, that'd be good to know. I don't know if I am or not. It's happened before. Just let me check this out real quick and we'll continue. So the crust is composed of two rocks. The continental crust is mostly granite. The oceanic crust is basalt. Basalt is much denser than the granite. Because of this, the less dense continents ride on denser oceanic plates. Moho discontinuity is this yellow line in between the mantle and the crust, basically. Right. So the idea is that the mantle circulating because of the liquid outer core, causing the magma to rise, and it's developing the mantle into this putty-like substance that can kind of circulate towards the continental crust, which is going to push it down, and then this is a process of subduction that they believe. So in plate tectonics, the rising mantle forms continents that slowly break apart into plates and subduct under one another over the course of millions of years. I'm just giving you the standard mainstream theories. There's some more views of the ocean floor and what that would look like. The boundary between all the continents and the ocean is this mid-oceanic ridge. It marks the origin of the formation of the continents in either model, either in deep time or from the perspective of a global flood where the mid-oceanic ridge was formed catastrophically. A progression out from a coastline anywhere on the globe will steadily decline for around 300 to 600 feet before a sudden steep decline of around 12,000 feet. So let's summarize the pre-flood model. You have a 30-mile crust approximately. I'm using this from the book In the Beginning, Compelling Evidence for Creation and the Flood, written by Walt Brown, who has a PhD in engineering. So he is estimated, according to his calculations, maybe around this ballpark. Okay, that's all I'm saying. It's just a theory. So 30 miles, approximately, the crust of the earth before the flood, with the region in between the crust and the mantle of 50% of today's oceans. And then you have the mantle, which is hard rock, the core, which is melted rock. The theory is that rapid convection occurred by a sudden uplift that lasted several months in the mid-Atlantic area before the flood. So, at the time of the flood, there's going to be a rapid uplift. The mantle would be that black line, okay, that circle. Okay, you have the inner core inside of that. Well, that mantle is going to come up above the white region, the crust that surrounds it, up and through it. This would rapidly form the continents. Hard rock of the pre-flood mantle will rise to the surface through an opening or rip in the crust. That's the 40 days and 40 nights of rain. Eventually it gets so wide that, it stops spewing into the atmosphere because the ocean level is too deep. but the water is still being generated just from gravity itself, and the continent's going up and down, squeezing the dirt and the rock and the water out from those subterranean chambers because they're collapsing. Um, as the walls of the ruptured crust widen, pressure is relieved from the mantle, and the melted inner core wants to rise. When the gap is wide enough, the magma will erupt through the mantle. A lot of magma being spewed up as the mantle begins to rise up. Here's a hypothesis. The heat from the inner core uplifted the mantle in the mid-Atlantic and created a rupture in the crust that encircled the globe. This caused the material on the Pacific side of the Earth from the mantle and the crust to sink down into the center of the Earth, forming today's solid core. The soft outer core is the pre-flood core that expanded around the intruding deposits of iron and nickel that derive from gravitational attraction acting upon the heavy elements according to density. So what I'm basically saying is that when the mantle rises up through the crust, this happens first in the mid-Atlantic area. Okay, so on the opposite side of the Earth is the Pacific. So if you see the mantle is rising up, well, then that's creating a vacancy in the center of the Earth, an expansion of what would already be a liquid inner core. It just expands, but then that pools on the Pacific side. And what that's doing is taking the Pacific side, the material of the Earth, the deepest points of the Earth, it's kind of basically the mantle on the Pacific side, and pulling it in towards the core. If you look at an oceanic trench or a subduction zone, it will always follow a coastline because this is a process of two plates, like colliding. Here's a bunch of ridges and trenches that you can see following coastlines. All 7 continents are surrounded by a great depression in the earth that's filled with water. It's called the oceans. So in the world, you have 7 oceans, 7 continents. The conclusion is that the mantle rose, and this is not the conclusion of the video, but the conclusion of the summary of this up until now. The mantle rose up through the crust until it reached around 2,000 feet above the crust. So this is happening first in the mid-Atlantic area. And the act of the uplift and the force of gravity acting on the crust caused it to slide off of the mantle and eventually compress by sudden deceleration from the grinding halt of the granite crust as it contacted the mantle, and this compression even condensed the crust into an average thickness of 12,000 feet high. So what's happening is a sliding process, the continental drift phase, the uplifting of the mantle causing the crust to slide off. And now on the Pacific side, though, it's going to pool on the Pacific side. And so the Ring of Fire, goes from South America across North America, Japan. I mean, it's like the most volcanically active place in the world. It's a trench, this Ring of Fire is actually a giant trench. And so this is the point where the crust of the earth rapidly decelerated. Like if you push a rug up against a wall, it's going to buckle, fold, and compress. That's what the earth is doing. And so at that point, you're generating tons of magma, melted rock, because of all that heat and pressure. And that's all going to be pulled towards the center of the earth. The most dense of that material would be the iron and nickel, which will go directly to the core, creating a solid iron and nickel core. And that's the hydroplate model, essentially, for this compression event, the deceleration of the continents, because they're being pushed like in the direction of these arrows here, off of the rising mantle, which would be the mid-oceanic ridge. The compression point here is the ring of fire that I just showed. The generated magma formed the mantle, uh, sinking down into the core and circulating up towards the mid-Atlantic, created huge plumes of magma that escaped through the mantle. So there's thousands of volcanoes and trenches, actively volcanoes. I'm pretty sure, like in the Pacific, on the Pacific Ocean floor. This is all from a rapid circulation of, the magma. Oceanic trenches are several times longer than Grand Canyon. They can be as deep as 6 miles below sea level. They would be the world's leading natural wonders if water did not hide them. And the center of the ring of fire in the Pacific Ocean is directly opposite of the mid-Atlantic, so that's why it's there. That's why these huge trenches exist, because the core of the Earth is kind of creating a hyperconvection current as the core expands because of the uplift of the mantle, you know, in the mid-Atlantic region. It uplifts, pulling on the Pacific side of the Earth, dragging down all that molten material, the ring of fire here. And then in other places of the world, and all of the trenches. This is the origin of them from the perspective of hydroplate. So you'll have like the points of compression on the continental crust and the oceanic crust, and you can have shear stress, and that's essentially what's causing, all that melted rock to accumulate along that line. And then it will be pulled towards the center of the Earth. So in the past, during the flood, during the compression event, you have what is known as continental drift, where plates sliding off of the rising mantle. They're sliding off of the mantle until a sudden deceleration that compresses them. And that would be like a box. You put a box and float it on the sea. It just bobs up and down. And that's the consistency of the crust of the Earth as it's sliding off of the rising mantle. Whereas today, you have a continental shift where changes in the Earth's gravity and equilibrium cause the crustal plates to shift, like putting a box not on the water, but on a ship that is on the water, So you put it on the ship's deck, and it kind of just shifts around if there's heavy movement. And that's the equivalent of what the continents are doing today, whereas at the time of the flood, they would have been more like that box on the sea, drifting. Now, material lost from the inner core as the melted rock rose to form the mid-Atlantic ridge was replaced by the mantle pulling on the Pacific side under and into the core. So nearly 80% of all volcanic activity is concentrated along the Ring of Fire. Over 80% of all earthquakes occur in this region, and the conclusion basically is that something dramatically has greatly disturbed this region. I mean, there's no question about that, right? Can't question that. I think that the easiest explanation is a rapid subsidation rather than like a pulling, or it is a pulling, but not like it's being forced down by the continental crust. And this is a part of it, but for different reasons. You have, instead of the oceanic crust being pushed under the continental crust, it's really being pulled, and so it's a subsidation rather than a subduction, and we'll get into detail on that in a second. But it's happening along that region, the Ring of Fire, and along other trench areas in the world. The Kuril Trench, Japan Trench, the Puerto Rico Trench, the Mid-American Trench. I mean, you got all these trenches, and they were formed by the same process. The rising of the mantle from the rupture ripped the Earth from end to end, starting at the Atlantic. The horseshoe-shaped region of the Pacific continents was created from the compression of the continents during deceleration. This created heat along what would be the continental edges, creating the horseshoe shape, and the granite crust above the Pacific floor was sheared off and subducted. So the mantle, according to Pangaea, rose slowly and formed the continents, which were once and later split apart by millions of years, drifting, called continental drift. And this is the, modern plate tectonics. They will say that it still is drifting, because it is a shifting. They would acknowledge that, but it's like a slow process, that just continues over millions of years at the rate at which it's going now, and eventually develops these large changes. So it just drifts over millions of years. The hydroplate theory would suggest that the continent slid off of the mid-oceanic ridge, rapidly. Like it wasn't like a slow spreading process, it was a rapid sliding event. The lubrication is the water, and then the deceleration develops into magma and trenches. So Pangaea model says 200 million years ago, all the present-day continents combined to form a single supercontinent called Pangaea. And it's the same as the pre-flood model, except all of that water is under it's much bigger, than their model. And their model has all kinds of problems with it. You gotta rotate North and South America one clockwise and one counterclockwise, and you have to entirely remove Central America and shrink Africa by like 35% just to make that thing work. So, but let's get into some more on plate tectonics or subduction. Let me get a drink. Let me check, actually, take a quick break here. I'll check the comment section out, see what's going on there. All right, so no action in the comment section yet. Everybody's probably asleep. That's all right. I'm going to keep this thing going. So you can look at Claus, I can't pronounce that name, Regner, PhD in Theoretical and Applied Mechanics, PhD in Geophysics as well. Science, Volume 294, The Initiation of Subduction Criticality by Addition of Water, ? Says the initiation of subduction remains one of the unresolved challenges of plate tectonics. And so plate tectonics of modern theories, how just a slow and gradual subduction can occur, has a lot of problems. Robert J. Stern, PhD in Geoscience, says, in spite of its importance, it is unclear how subduction is initiated. Subduction, initiation, spontaneous, induced. That's Science Letters. It's another journal, volume 226. Science, volume 294. The intense pressure needed to force the front of the oceanic plate under the continental plate would exert equal pressure on the midsection and force it up, causing it to buckle. So yeah, it's going to buckle up, along the coastline, like the modern mountain ranges are going to form when this process is initiated. And that was several people with a PhD, I'm sure. So you can see there Klaus Regner, Dave Wen, Joy Braniand. They're just all explaining the initiation of it. These authors propose that ocean water may have softened the Earth's crust by breaking it along a narrow band all around the Earth. And so, to make this process easier geophysically, you just soften up the Earth, at the subduction point. So, just by adding water, we obtain a narrow fault-like zone for lithosphere separation, but a sound quantitative description does not exist. So they're saying, we can do this hypothetically or theoretically, but we can't actually replicate that much power, that much mass. It's really not repeatable, but theoretically you could do it if it was softer along those reasons. But the fault line created by water, plate tectonics. The entire seafloor is sliding under another plate. That's according to modern plate tectonics. This happens over deep time. According to hydroplate theory, the material that once filled the trenches subducted into a convection current in the soft pre-flood core. So again, that pre-flood core, it's expanding, and all that material from the trenches is being pulled in. So I'm going to give you several, pieces of evidence. We're going to skip a lot of them, or not a lot of them, but some of them, on why subduction is not correct. Let's just put it professionally, I guess. According to Scientific American, Volume 221, Henry William Menard, PhD in marine geology, he said, it would seem that the sediment sliding into the bottom of the trench should be folded into pronounced ridges and valleys, yet virtually undeformed sediments have been mapped in trenches. And so this was, they were actually mapped by David William Scull and his colleagues at the U.S. Naval Electronics Laboratory Center. Furthermore, the enormous quantity of deep oceanic sediments that has presumably been swept up to the margin of trenches cannot be detected. So these fine detailed folds and ridges that should be in the trenches, and a whole bunch of sediment and dirt that should be there, because the process of millions of years, a lot of dirt and stuff is flowing into the oceans, and that's creating a lot of dirt, when you have this process of one plate crushing into another as it subducts under it, that a lot of crumbled rock develops, and so it's really not a trace of any of that there, relatively speaking. It virtually doesn't even exist. It's completely vacant, and these ridges that you'd expect to be there do not exist. So translation to that is that the sediment at the bottom of these trenches are undisturbed, and the volumes of deposits is relatively small. So with that translation in mind, let's look at Science Volume 358. Julia Rosen, researchers also want to get a glimpse of the subduction slab itself. There's a couple 100 million years of oceanic crust going down, and we don't know where it went. Now, more research, I believe, has been done, and we've been able to actually detail this out and graph it. It appears to be relatively cold slab of rock, where as if this cold slab of rock has been there for millions of years, it should have basically matched the surrounding temperature, which would be the mantle, and it hasn't yet. It's still soft. So that would indicate that material was pulled under relatively recently and catastrophically, all at once, because it's all the same temperature as well. So according to Geological Society of American Bulletin, Volume 81, slippage of the oceanic crust beneath an overlying trench fill is unsupported by observational as well as theoretical data. So there you go. There's missing dirt there. And then there's also the certain folds and stuff that should be there, which I guess we won't get into detail on that. But overcoming the problem of a log jam as well. You have a bunch of rock, that's trying to you're trying to force one slab of rock under another, creating a log jam problem. Overcoming this problem would generate enormous volumes of magma, and the Ring of Fire is evidence that this occurred on a global scale. So there was a logjam problem, but it was overcome by the extreme pressures of a global flood, the compression event. Otherwise, the current process of, slow and gradual subduction is not enough to overcome this logjam problem. It's like getting two washboards and trying to move them against one another, like slide them over one another. It can't be overcome without producing huge amounts of magma. That magma is available, it's present, but it can't be from the normal process. The pressure that is exerted today from subduction cannot do that, not even over deep time. So hydroplating is the sliding of the crust by lubrication of water off of the rising mantle. The compression event is the sudden deceleration of the sliding plates by loss of that lubrication. If you look at their model of subduction, it kind of looks like this, but this can only occur along a straight line, you see. If you curve it, it's going to have different effects. It's going to have like these folds, like these massive curves, and like it's going to have a lot of wrinkles because it's folded. If you have something, you know, if you have one plate going under another, but it's along a curve, we have a different effect going on here, kind of like trying to rip a phone book in half. Creates like a fold there, which you don't see. That's not available in the evidence. So conventional model is that the oceanic crust is being pulled by the convection currents of the liquid outer core, heating up the mantle, causing it to circulate like a putty, pulling the oceanic crust under the continental crust. And this is what creates the magma and the plumes, But again, problems with that. There's a arc shape here. And so why would there be in a specific arc shape? Is this because of an extreme pulling force? It had to be an extreme pulling force, obviously. But is that extreme pulling force being exerted today? And it's not. You'd have to have a lot more energy. So with the hydroplate theory, this extreme pulling force occurred, within several months as the pre-flood inner core is expanding. So it creates a cusp shape depression on the Pacific side of the Earth, and it's huge. You could fit every continent in the world in the Pacific Ocean, actually. But if the heat of the inner core was released up to the surface in the mid-Atlantic, the Pacific side would actually deflate. You get a ping pong ball and it produces the same shape. When you put your thumb on it, you slam it down. It's going to produce, it's going to indent and produce a cusp shape very similar to the Pacific Ocean. If you put that same deflated ball onto a pot of boiling water, it will inflate. So it was deflated at the time of the flood, the Earth itself. And so that is essentially the compression event. Here's the conclusion. The Pacific Ocean appears to be a deflation in the Earth, and so it was subsided along the trenches. The material was subsided to go down to a lower level. Subduction is a creeping mantle slowly descending over millions of years, and subsidence is a strong convection current overcoming gravity. According to University of Bristol, ScienceDaily.com, most of the precious metals on which our economies and many key industrial processes are based have been added to our planet by lucky coincidence when the Earth was hit by about 20 billion tons of asteroidal material. So they're saying that, this is how the Earth formed. It was bombarded by meteors and it continued to be bombarded throughout its history. According to Science News, Volume 156, meteorites, he notes, contain 10 times as much exxon relative to other noble gases that occur in Earth's atmosphere. In addition, the relative abundance of exxon isotopes found in meteorites doesn't jive with the pattern found on Earth. If meteorites did deliver most of the water to our planet, they also would have provided exxon. So you can do the same thing with comets. You tell what they're composed of, and it doesn't look like the Earth was formed from a heavy bombardment of these asteroids because it would have a different composition. And if the water came from comets or meteors and asteroids, then, it would also have a different composition. So there are problems not only with subduction, plate tectonics, Pangea, but there are problems with getting the material of the Earth itself from a molten state. In fact, granite, cannot even be simulated in a laboratory. Let's see. In some places, the mid-oceanic ridge, these ridges will actually intersect with trenches. But how can a mountain rise and subduct at the same time? You have the East Pacific Ridge and part of the Ring of Fire, along North America, there's a trench, and that ridge intersects it. That's conflicting, in nature. If there was a rapid uplift of that ridge and a rapid subduction of all that material along the trench, then you could have this happen. But if the mid-oceanic ridge, if this ridge is uplifting over deep time, while at the same time material is being pulled under, how's that happening at that specific intersection there? It doesn't seem geophysically possible unless you look at it from the hydroplate theory. So along that blue line, that's where the convection begins, in between North and South America, Africa, and Eurasia. This is where, the heat is rising, and so the Pacific would then deflate. I will just summarize the pre-flood model of the Earth's composition in general, and then that will be the end of the presentation. The pre-flood model, you have crust that is mostly granite and metals, and then you have the moho, which would be in between the crust and the mantle of most of today's oceans. The chamber floor would be the mantle, essentially, and then the core is going to have melted mantle rock. It's going to be liquid inner core, which at the time of the flood, at the compression event, it will develop iron and nickel solid core. Now, after the flood, the crust is still, mostly granite. It's been shuffled around. The oceanic crust is melted rock that quickly cooled. This would be the rising mantle, intruding all the mantle material onto the ocean floor. And, when magma is rapidly introduced into water, quickly cools, forms basalt. So that's what the ocean floor is covered with. And then you have the moho in between the crust and the mantle, evidence of a sudden separation of crust from the mantle for probably reasons that, we don't want to get into right now. But the mantle is the pre-flood rock, it's the same. The outer core is pre-flood core. made of melted mantle material. So what used to be the core of the planet before the flood, which it's just a liquid inner core. Today it's iron and nickel because of what happens as a result of the flood. The iron and nickel inner core is from the subsidation and the hyperconvection. Now I know that that was a little technical, and you can go back and watch it a few times if you want. So I made it as comprehensive as possible, and I did it like in under an hour. So that works out. We'll take a little intermission here and give people time to join the stream if they want. You can hop in the box and comment on anything that was said in the presentation or share any thoughts in general. So I'll be right with you. Thanks everybody for tuning in. Stay in prayer. God bless America. My name is Christian Sylvius. Peace be upon you.